আচ্ছা স্ক্রিন কি দেখা যাচ্ছে? Can everyone see the screen?
জি ভাই দেখা যাচ্ছে।
Okay, so we are starting with a new chapter, application of DFT. This is from the end of our previous chapter, that was DFT. We finished up to uh, the polar notation, polar nuisances, all those things. And today we'll be starting with the applications of DFT. So this chapter is just all about what DFT allows you to do. So normally what we have seen from the previous chapter is that DFT gives you access to the frequency domain of any signal. Before that we have been doing all those things in time domain. Now we know how to get to the frequency domain. So this chapter is basically just going to talk about what information can be obtained from the frequency domain. So what can you do if you obtain the frequency domain? Now what are the things that are unlocked for you? The first thing that DFT does is calculates the frequency spectrum. So this is just what we have seen in the previous chapter. This is nothing new. So it gives you direct examination of information encoded in frequency. Or frequency means directly the complex numbers, or if you convert it to the polar form, then you get the phase and all those things. And the second thing that DFT does is it allows the systems, it allows you to find a system's frequency response from the system's impulse response, and vice versa. So this one is very important, and this one will come later in this chapter. There is we have talked about impulse response. Impulse response is the basic, is the main thing that defines a system. Any system, whatever it is defined based on its impulse response, right? Every system has its own impulse response. Whenever you give something to the system, it gives something out. So a system is, it takes a signal, it produces another signal. How does it do it? It has its own impulse response. It performs convolution with it. Now one might think that this convolution, this happens in the time domain. So what would this same system do in the frequency domain? So this is just what DFT allows you to calculate. It gives you a new perspective. That is, in the time domain, if its behavior is this, that it performs convolution with something, in the frequency domain, what it will do is, similarly, it will, instead of doing this with its impulse response, it will have its own frequency response, capital H, suppose. And similarly, it will produce from one frequency, it will produce another frequency. If you give some frequency information, it will produce another frequency information. So how is it going to do it? That is what we are going to be talking about later on in this chapter. So just a heads up, since in the time domain we have told you that it performs convolution, in the frequency domain one can only guess that it will do multiplication, because in the previous chapter, uh, in chapter 8 DFT, at the later part, we have discussed about the duality of time domain and frequency domain. And we have also said that any convolution done in the time domain is equivalent to doing multiplication in the frequency domain. So from that, you can already surmise that if a system performs convolution in time domain to get an output, similarly, in the frequency domain, in order to get an output, it will do the multiplication with its corresponding frequency response. So this is what we'll be talking about later on. LMS access করতে পারতেছে না একজন. Okay, I'll be giving your attendance at the end of the class. Do remind me again. Okay, 39. So where was I? Okay, then the third point. So this is the second thing, that it allows you to use the frequency response from now on instead of the impulse response, which we used in the time domain. So now the third thing is that the DFT can be used as an intermediate step in a more elaborate signal processing technique. This one we'll not be talking about much, but this is just clarification for you guys, that there is a faster method of doing convolution. We have seen convolution in the time domain. We have already executed it in our exams also. But there is a faster method of doing convolution, and that can be done in the frequency domain. This is called the FFT convolution. And for this, you need the DFT, obviously, because you have to convert it to the frequency domain before you perform this convolution. So this is just the third application of DFT. So all these three applications are basically the main topics of the main topics here, and we'll be mainly focusing on the second one at the later part of this chapter. So now let's see a scenario where DFT and the overall use of frequency domain becomes helpful for us. So here an example is given. uh, this is a long story, but the main thing that we will have to focus on, I've just marked it. So focus on these main things. There are lots of things here, but you don't have to go through everything here. So the scenario that they created is basically, suppose you are trying to investigate the sounds that travel through the ocean. Basically, you're trying to investigate some underwater sound. Okay, some frequency and everything from underwater sounds. Something similar was given to the lab group A in this week's lab. The audio signal that I gave was similar to this, some underwater sound. So for that, what you would have to do is, you would have to, in order to get that sound signal, you would have to place a microphone in the water, and the resulting signal will be amplified to a reasonable level so that it is uh, the main information can be extracted. So now, after you do all these things, what will you get? When you visualize it, when you plot it, when you take the amplitudes and convert it to some form that you can visualize, and you plot it, what you get is, you're going to see a noisy waveform that conveys little information to the eye. So this is seen from, okay, I'll have to come back to this page and go back and forth between these two pages. So this is the first thing that you're going to get. Okay, so this is the first thing that you're getting when you plot the amplitude values of the sound signal from the ocean. Now, the problem that will happen later on is that from here you cannot understand anything. So you're trying to get some important information, but this just a bunch of amplitudes do not give you any important information. So now what you're going to do? So this one just this example, this whole scenario just shows a bunch of a sequence of actions that you can do to get meaningful information from any signal. So here, uh, since you cannot understand anything directly, so what you do next is, you multiply this signal by a smooth curve called a Hamming window, and we'll be talking about the Hamming window later on in the digital filter chapter. Also, if you want to just know what a Hamming window is, you can go to chapter 16. Chapter 16, equations 16, 2 and 3, 1, 2 and 2a, and figure 2a. These three things just talk about the Hamming window and the Blackman window. Okay, so there are two windows specifically used for reducing noises, uh, end noises, Hamming and Blackman. And the equations for them you will find in this chapter, chapter 16. So Hamming and Blackman, the equations were something like, these were just basically some modified cos waves. This is also a different version of a modified cos wave, cosine wave. You can see the equations here. The main thing that we are going to discuss about is the use. Why do we multiply with Hamming window? After we get this, time domain signal, why are we multiplying with Hamming window? By the way, this is the figure of a Hamming window, the plot of Hamming window. So why are we multiplying with this? The reason will become clear later on, but for now we can just tell you the main thing, that what Hamming window does. When you multiply any signal with a Hamming window, the ultimate result is, in the frequency, in its corresponding frequency domain, it will have the end uh, frequencies, end noises reduced. That means everything will have, in any signal in the frequency domain, there are some end noises. By end noises, I mean in the first part and in the last part. In the middle part, the frequencies are almost what you're supposed to get, but in the first part and the last part, there are lots of end noises, some ripples. Okay, so instead of getting the actual values, you get some ripples. So in order to reduce these ripples, this Hamming window or Blackman window, these two windows may be multiplied with the time domain signal, so that in the corresponding frequency domain we do not get this. Also, you can just see the result. If this time domain signal is multiplied with a Hamming window, this is the result. Okay, you can see that these amplitudes are minimized from here. These two amplitudes are minimized, and the main signals in the middle are more easily visible. So this is the step that happens after you multiply a Hamming window with the time domain signal that you get. And then what you do is, so here this was supposed to be a 256 point signal. So here we are considering that the number of samples that we took from our microphone was 256 point. So here you can see there were 256 points here. Okay, from 0 to 255. There were 256 point. This was a 256 point signal. So when you multiply with a Hamming window of 0 to 255 range, then you get a similar 256 point signal where the end noises are reduced. Then you take the DFT of it and convert it to polar notation. So what are you going to get? You're going to get 129 point frequency spectrum. Okay. So after you perform DFT on this one, this is the result that you get in the frequency spectrum. So you can also notice that directly performing DFT still does not give you any much important information because there are lots of noises even in the frequency domain. So which one is actually the peak that you want and which one is a noise? This is difficult to understand. So for this, there is one technique that they suggest applying for such scenarios. That is, uh, okay. So one thing is that this looks like a noisy mess. So what can you do in that case? This is happening because there is not enough information in the original 256 point signal. So using a longer DFT will also not help in this situation. By using a longer DFT, we mean that you can increase the number of points from 256 to you can have a long signal and you can perform a longer DFT on this. Right? From 256 point, how can you have a longer signal? You can just pad it with zeros, and then you can perform a longer DFT. So instead of having a 256 point DFT, this will be maybe 1024 or 2048 point DFT. You can have something like that. So in that case, what you will have is that the range of this will become larger, right? So that means the resolution will be greater. So if the resolution is greater, it will be easier to distinguish because there will be more gaps in between the peaks. There will be more gaps. So one might think that this will be helpful. Having a longer DFT will allow me to get the useful information from amongst the noises, but still it won't be useful. That is what they are saying. That is because even in those locations where there are useful peaks, there are still noises to the left and right always. So these random noises will make it hard to identify where the actual peak is located at. So for this reason, instead of using a longer DFT, what they suggest is they break the input signal into multiple 256 point segments. So this is the main important part here. So what you're supposed to do is, suppose you're uh, listening to some uh, noisy environment, maybe the traffic, and you're trying to obtain some frequency information on something from the traffic sounds. So what will happen is you can take a small sample, a small duration, a small time frame of sounds, and maybe that is a 256 point signal, and you perform the things that we have talked about before. Okay, multiply with Hamming window, then perform DFT, then you get that particular thing. Now what you can do is you can repeat this experiment multiple times. Take the same 256 point samples again, maybe at different time intervals, at different times of the day, and then you have many 256 point uh, samples, signals. So what you do is you do the same procedure on all of them, on all these 256 point segments, and then you perform an averaging of them. Okay, so when you do that, the noises will get averaged. The main important information will get more weight now, and they will become more prominent instead of the noise. So this is also a very important thing that you will see in DIP. Those who will take the DIP course, you'll see some similar experiment in one of the chapters where it will be said that maybe you're looking through a telescope. Okay, you're looking through a telescope towards an faraway planet, and the image that will be generated by this, if you use look at it for a long time, and take snapshots after a regular interval, each of the snapshots will have some grainy effect. Okay, so the image of the planet will have some, like, it is very expected that there will be very it will be grainy because there are lots of cosmic noises and radiations from outside, and those will interfere. So the whole image will be very grainy. But what you're doing is you're taking the image for a long time, taking snapshots of uh, a lot of snapshots over a long time. So what happens is you have this same image but with different grains in that means different noises at different times. So if you take an averaging of all of these snapshots, what will happen is the grains will get averaged. So at some point it was a bit more than that, a bit more. This amplitude was a bit more. Here maybe the amplitude was a bit less at this pixel. So some plus, some minus, this will get ultimately averaged and this will become close to zero. Ultimately, this is what happens. Any kind of Gaussian noise can always be minimized and made close to zero if you perform an averaging. If you take a lot of samples and perform averaging. So this is the main idea. So if you take the same image, uh, take the same snapshot multiple times and perform an averaging of them, the noise will be reduced, and the main thing, the main this planet or whatever it is, that particular thing will get more prominent. Okay, so this is the main idea. So this is what we are also doing here in the audio case. This is just the audio case. So we are taking the same signal, similar type of signal many times, and we are doing the same thing, multiplying with Hamming window, performing DFT, and we are taking an average of them. So when you take an average of them, this is the result that you get. This is the average spectrum. So the noises, those which are the noises, they will get reduced because they, in some case you're going to get plus noise, in some case you're going to get minus noise. If you take the average, it will get reduced and it will be something like this. The actual value will become more prominent. So this is the first peak. This is the actual value. It got more prominent. All these other peaks, those were not actually peaks. Those were noises. Okay. So one peak, there's also some small peaks here, and you get another peak. So now this is the result that you get after you perform the averaging. So we have completed up to this part. So now we can get some important information. So other than this, there is also another method, this a second method for reducing spectral noise. So here what we did is we just reduced the spectral noise. Okay, so now the second method for reducing spectral noise, that would be by taking a very long DFT of a 256 point signal. So how would you take it? You just quad it with a lot of zeros and you perform a long DFT where the value of n is large, something like this. So the corresponding frequency spectrum would also be high resolution, and by 2 plus 1, it would still be a lot of samples, more than the actual number of samples. The actual number of samples is 256, but the number of frequencies that we're allowing is this much. So like I said, if you have a lot of frequencies, you'll have a lot of gaps in the middle. So it will be easier to distinguish between the peaks. So what it does is after it takes a large DFT, then it makes the corresponding frequency spectrum to go through a low pass digital filter. And we haven't talked about digital filter, so you won't know what it will do to it. For now, just know that it will smoothen out the signal so that it reduces the noise, and only the uh, main peaks that are necessary, those will remain. So it will reduce the noise at the expense of resolution. So which method should we use? The first method that we have discussed about uses the Hamming window and then performs DFT, short DFT, and the second method performs a longer DFT and uses a filter. So which one will we use? It depends on the situation. The first method is easier, but the second method has potential of being better, of giving a better performance because the filter itself can be tuned. So this is just from an application point of view. Which one will we use? The main thing that we need is this ultimate result, and we know how this one came. Okay, so this one will be used later on. So all the story and scenario, everything that was said was to direct just to get up to this spectrum, because the important information will come from this spectrum. So now we will see what are the important information we can get. So now we can see that figure 9.2 shows an example spectrum from our undersea microphone. So not this one. We are coming to, so we are using that same figure here, but here some important information are noted out. So we'll see what these are. So if you ignore the sharp peaks, by sharp peaks I mean these ones. If you ignore them, then the other things that you are getting here, between 10 and 70 hertz, the signal consists of a relatively flat region. This is called the white noise. So there are a bunch of stuff we can get from this one figure, as you can see here. From this one figure, there are lots of things we can get between 10 and 70. Okay, within this range, 10 and 70, there is a relatively flat region, right? So this is called the white noise region. So this region is called the white noise region. And this one results from some random noise. Okay. It contains equal amount of frequencies, uh, same as white light. And then there is another region, the random motion of electrons in electronic circuits also produce white noise. So these are just some other examples of where you can get white noise, and due to what kind of scenario white noise may come. So these small perturbations, what are these resulting from? So in this scenario, this may come from, okay. So in this scenario, this white noise may come from the analog electronics that is measuring the sound, underwater sound, or the ocean itself. Any one of these may give white noise. So in some other scenarios, white noise may come from the electronic circuit itself, or so, for example, the sound that you hear when water spray hits the shower floor. That is also another example of white noise. So these are just some examples of white noise. You will always get some small disturbances like this in the frequency spectrum, but these do not refer to the actual frequency. These peaks refer to the actual frequency, but there will always be some small disturbances like this. Okay, now there is another region above 70 hertz. The white noise will gradually decrease in a very exponential manner, as you can see here. It will reduce exponentially towards zero, and this is the result of a roll off of the anti-alias filter. An ideal filter will pass all frequencies below 80 hertz and block all frequencies above. But since this we cannot use ideal filters in digital systems, so it will have some gradual fall off instead of like gradual just becoming zero. So the actual thing that was supposed to happen here is that you are supposed to get something like this, and at this particular place you're supposed to get instantly jump to zero if it were an ideal filter. But since this is not an ideal filter, so it won't just pass it like this and then instantly make it zero. It will have a fall off and it will gradually get it to zero. This is the non-ideal case. The ideal case would have been it will pass everything, and at this particular 80 hertz mark, it will just jump to zero. Okay, so okay, then there is also another region below the 10 hertz. So that one was above 70 hertz. So now we go backwards. So below 10 hertz, the noise is very high, and this one happens due to a phenomenon called the 1F noise. Okay, so this one is not understood even now. It is not understood why every kind of electronic devices produce this kind of noise, this 1F noise. Okay, so what is the 1F noise? This part, this high noise, but this is not actually referring to any frequency in your system. So peaks refer to the fact that there is a frequency here. Okay, so every peak means that this particular frequency is present in your signal. But even though you're getting a large peak here, this is not actually referring to any frequency that is present in your system. This will always be there in almost every kind of scenario where you measure something with some electronic equipment. There will always be some noise at the early frequencies, the beginning region. So this one is called the 1 by F noise, and it is still not understood why this kind of noise is found in electronic systems. And there are lots of speculations of whether you can actually go through this particular paragraph and see, but it won't give you any kind of definitive idea that this is the reason for 1F noise, 1 by F noise. So it is still a mystery. Okay, now we come to the sharp peaks. So by sharp peaks we mean these things. So these are the ones that represent the actual frequencies that are present in our signal. So what is this saying to us? So the easiest one to explain among the sharp peaks is the 60 hertz, the peak that we get at 60 hertz. So this one comes from uh, electromagnetic interference from commercial electric power. So why 60 hertz are we? Why are we assigning 60 hertz as the coming from electromagnetic interference? That is because I think we have heard from our intermediate level current electricity, maybe AC current, is that most AC current always work on 60 hertz range. That is the electromagnetic interference will, if it comes from outside, it will be of 60 hertz. So if there is a peak in any system, in any signal, you can sense that there may be multiple peaks, but if there is a peak, there will almost always be a peak at 60 hertz. That is, and you can understand that that one comes from, it may happen that the signal itself has a peak at 60 hertz, or this peak is actually coming from electromagnetic interference, and the electromagnetic interference is almost always at this range, 60 hertz range. Okay, so this is one. In this case, we are considering that this is coming from electromagnetic interference, and there is another peak, and this is the actual frequency of the signal. Uh, there is a strong peak at 13 hertz, as you can see. So in this location, there is a strong peak. Okay, so this one is actually referring to the actual frequency of the signal. And there will also be weaker peaks at 26, 39. So all multiples of this of 13. There is at 26, you can see that there is a small peak here. Also at 39, there is also another small peak here. So in all multiples of 13, we will get peaks as well. The peak at 13 hertz is called the fundamental frequency. Okay, so we have already said what fundamental frequency is in our in the other book, in Proak's book. So that was in even uh, that was from a kind of equation perspective. So we had some cos something, okay, 2 pi something, uh, and from that we found the fundamental frequency, right? So there was k by n. We could, if we could represent it using something like this, if that f could be represented using k by n, then, and if they were co-prime, then the n would represent the fundamental frequency. That was from an equation perspective, from a kind of function perspective. But now we are seeing it from frequency domain perspective. So in the frequency domain, the sharpest peak that you will get, that will most likely refer to the actual frequency of the signal, and that will be the fundamental frequency. The fundamental frequency will have the sharpest peak, and any multiple of it, that means for different values of k, all those particular frequencies will also have peaks, and those are known as the harmonics. Okay, so the peaks at 26, 39 are referred to second and third harmonic respectively. So there are infinite harmonics, second, third, fourth, there are infinite harmonics, but you won't see any of them. Why? So you would also expect to find peaks at other multiples of 13 hertz, such as 52, 65, 78. But you do not see this in here. Why? Because these are getting buried under the white noise. So this region of white noise, the small disturbance, so this is actually uh, taking control of the small peaks. So the small peaks are also here, but those will seem like noise. So it will be very difficult to distinguish those peaks from the white noise, the small disturbances. But those are also here. So this was all about the characteristics of different peaks and the different noises that you can get. 1 over f noise, the white noise, the anti-aliased filter roll off, and the main peaks. Okay, so now one problem that can happen. So we are done with this particular uh, frequency spectrum. What are the things we can get from this frequency spectrum? We already know now. So now one problem that can happen is that if there are peaks very close together, such as this. Okay, so in these scenarios, there are two factors that limit the frequency resolution that can be obtained. And the first factor is the length of the DFT, that is the value of n, capital N, we mean. So capital N is one factor that will determine how well you can distinguish the peaks. And the other, uh, okay, so this part is just explaining that having greater values of n allows you to have more distance between the peaks. Okay, because there are more frequencies in that means this horizontal axis will be larger, right? If the value of n is larger, then this horizontal axis range will be larger, even though it is always shown from 0 to zero point 0.5, but the actual value of frequencies that we are allowing is less here and it is more in here. So this one is for n equals 128 and this one is for n equals 512, and the peaks are actually the same for the same signal. So these two peaks are for maybe one signal. These two peaks are also for the same signal that we were talking about here. But notice that here these two peaks were very close, and here these two peaks are relatively far apart. So why this is better? This is because in this location, if these two peaks are very close together, one problem that can happen is, suppose you have something like this and these two peaks are very close together. So what can happen? Maybe there are some other small peaks here, but there was supposed to be one single peak here, and you got two peaks very close together. So what problem may happen is that you might think, are these two frequencies the actual frequencies of the actual frequencies of the system, or are these two peaks coming from some kind of noise? It is very difficult to distinguish, but here it is easy to distinguish. Noises cannot come like this, right? Since you're getting two peaks relatively far apart, it is easy to understand. One frequency is in this location, the other frequency present in the signal is in this location. It is easy to understand. But here, it is difficult to understand because this may come from noise or this may come from the actual frequencies present in the system. Okay, so one thing is N, the capital N, which allows us to easily distinguish between frequencies. The second limiting factor is more subtle. So imagine a signal created by two sine waves, but only with a slight difference in their frequencies. So here it is saying that suppose the original signal was created using sine waves, which are almost equal. Okay, so these two sine waves are almost equal. So if you superimpose them, it will seem like these two are there is no two signals. This is just same signal. Okay, so I'm drawing the same signal one over another. Okay, so it is very hard to distinguish that these two are two different signals. There are two different signals in the same location if I superimpose them. Okay, so this will only become apparent when you take a lot of samples. Maybe after a lot of samples, you will see that they start to slightly gradually deviate from one another. And if you take even more samples, then you'll see that there is more deviation. Okay, so one will be here, other will be here. So this deviation, these two deviation will become deviation from each other of these two signals will become apparent in if you take a lot of samples to the right. If you take just a few samples up to this, if you take it and just perform anything on this, it will seem that these two signals are exactly the same. Okay, but if you take a lot more samples, then you'll start seeing the deviation from one another. So this is the second limiting factor. Okay, the length of the signal, not the length of the DFT. So the first limiting factor was n, length of DFT, and the second limiting factor is small n, the length of the signal. Okay, so this is what it says. Over a short segment of the signal, say a few periods, the waveform will look like a single sine wave. They will look exactly alike. But if you take the length larger, then it will start to become different. Okay, so this is distinct from the first factor because the length of the input signal does not have to be the same length of the DFT. So this one is actually important. So one might be thinking that if a signal is of if the value of small n, the number of points in the time domain is something, we are also going to take that many point DFT, but that is not always the case. If the time domain signal is maybe 256 point, we can always have a DFT of 1024 point DFT on it. Okay, or any kind of DFT on it, 2048 point DFT on it. For a 256 point signal, we can have that. How? We'll just have to pad it with zeros and make it equivalent to this. But we can always have this larger DFT on a smaller point signal. So this is the main point here. Okay, taking a 2048 point DFT produces a frequency spectrum with 1025 samples on a 256 point. So you can do this on a 256 point signal. The added zeros don't change the shape of the spectrum. They only provide more samples in the frequency domain. So this is the main idea, that you're adding zeros in the time domain signal, but you're not changing anything in the frequency spectrum. You're just increasing the resolution of the frequency spectrum. so the peaks will be more clearly distinguishable because they'll move farther apart. Okay, now the next question: what happens if the
ভাই
input signal?
যখন
Yeah.
প্যাডিং করতেছি আসলে তখন তো মানে আমি সেম জিনিসটার মধ্যে অনেক জিরো টিরো ঢুকাই দিছি, তা এখন তো আরো কম্প্রেস হয়ে গেছে, মানে মেইন সিগন্যালের জায়গাটা আরো কম্প্রেস হয়ে গেছে। তা ওইখান থেকে আইডেন্টিফিকেশন করাটা আরো হার্ড হয়ে যাওয়ার কথা না? মানে আমি জিনিসটা চড়া করলে তো আরো ভালো মানে
চড়াই তো করতেছি, কম্প্রেস তো করতেছি না। চিন্তা করে দেখো যে তুমি হচ্ছে এক্স কে স্মল এক্স মানে টাইম ডোমেনটাকে তুমি আরো বড় করে দিচ্ছ বাই অ্যাডিং মোর জিরোস। এটা অরিজিনালি ছিল 256 পয়েন্ট, ঠিক
হ্যাঁ,
আছে?
কিন্তু ভাই জিরো গুলা তো লেফট রাইটে প্যাড হচ্ছে, তাহলে ও মাঝখানে পড়ে আছে না?
লেফট রাইটে, হ্যাঁ, তুমি ধরো খালি রাইটেই প্যাড করতেছো, সাপোজ ফর
আচ্ছা।
সিম্পলিসিটি আমরা রাইটেই প্যাড করতেছি যে আমাদের আমাদের অরিজিন এখানে আছে, এখানে আমাদের অরিজিন আছে, এখানে অনেকগুলো স্যাম্পল আছে, এখানে শেষ হয়ে গেছিল 256 পয়েন্ট।
জি ভাই।
নাও ইন অর্ডার টু টেক 1024 point DFT on it, we are just increasing its length by until it matches 1024 length, ঠিক
জি
আছে?
ভাই।
করলাম। তো করার পরে এটা করসপন্ডিং ফ্রিকোয়েন্সি স্পেকট্রামটা কি হবে? অরিজিনালি এটার ফ্রিকোয়েন্সি স্পেকট্রামটা যদি ধরো এরকম ছিল, এখন যেটা হবে সেটা হচ্ছে এটার ফ্রিকোয়েন্সি স্পেকট্রামটা শেপটা এরকমই থাকবে, শুধু এটা মানে এটা স্কেলড হবে, ফ্রিকোয়েন্সি স্পেকট্রামটা স্কেলড হয়ে যাবে বিকজ আগে এখান থেকে এতটুকু ছিল আমার কত, এটা আমার কত ছিল 256 পয়েন্ট, so it was allowing 256 frequencies. Now it is going to allow 1020 এটার উপরে 1024 পয়েন্ট ডিএফটি নিয়েছি তো,
জি
so
ভাই।
it is going to allow 1024 হইলে
জি ভাই, বুঝছি
513,
বুঝছি, বুঝে
ঠিক
ফেলছি
আছে?
বুঝছি।
এটার মানে ইয়েটা বাড়াই দিছে, হরাইজন্টাল অ্যাক্সিসটা বাড়াই দিছে, ঠিক আছে? তো বাড়াই দিলে যেটা হবে সেটা হচ্ছে এটার শেপটা ঠিকই থাকবে, শুধু মাঝখানে মাঝখানে স্পেসিং বেশি হওয়ার কারণে this will just become scaled, this
জি
whole
ভাই,
thing
বুঝছি।
will become scaled. Okay, so scaled হলে যেটা হয় স্মল স্কেলিং এ আমার এই ক্লোজ পিক গুলো দেখা যায় না, বাট লার্জ স্কেলিং হলে তখন আমার পিক গুলো একটু ফার্দার আপ হয়ে যায়, ঠিক আছে? তখন এই জায়গাটা ভালো মতো বোঝা যায়। এখন কি বোঝা গেছে?
জি ভাই, এটা কি অনেকটা কোয়ান্টাইজেশনের সাথে মিলানো যায়? মানে কোয়ান্টাইজেশন আমি লেভেল বাড়ায় দেওয়ার মতো এখানেও
হ্যাঁ হ্যাঁ হ্যাঁ, ইয়েস
REX IMX বাড়ায় দিচ্ছি অনেক
ইয়েস
বেশি।
ইয়েস। তো ওই কোয়ান্টাইজেশন করলে আমাদের কি হয়, টাইম ডোমেইনে ইজিয়ার হয়, রাইট?
জি
স্যাম্পল
ভাই।
গুলোকে ডিস্টিংগুইশ করতে। আর এটা হচ্ছে ফ্রিকোয়েন্সি ডোমেইনের কোয়ান্টাইজেশনের মতো, যে আমরা ফ্রিকোয়েন্সি ডোমেইনে ফ্রিকোয়েন্সি গুলোর মধ্যে কোয়ান্টাইজেশন মানে ডিসক্রিটাইজেশনটা কত ইয়ে পরপর করতেছি, এটা
জি
হচ্ছে ওই এন এর উপর ডিপেন্ড করে, ওই লেন্থের উপর ডিপেন্ড করে, DFT length. So this is like, this allows you to have different levels of accuracy of the DFT, increasing the value of n or decreasing it. So acha, so what এখন যেটা বলতেছিলাম যে what happens if the input signal contains a sinusoid with a frequency between two of the basis functions? So আমরা এর আগের চ্যাপ্টারে যখন বলতেছিলাম আমরা সব সিগন্যালকে ক্রিয়েট করতেছি কিভাবে, using basis functions like cos 2 pi I by n এরকম কিছু একটা ছিল, একটা n এরকম একটা বেসিস ফাংশন ছিল, and there was another with sign, right? So these were all the multiples of this that we could use. So I এর value 0 1 2 এভাবে করে আমরা বাড়াতে পারতাম। So these are all the independent basis functions that we can get. So what if the frequency that is present within the signal is not exactly an integer multiple of 2 pi by n? যদি এটা না হয়, মানে এটা obviously possible যে আমার ভিতরে এমন একটা সাইনোসয়েড আছে, that signal can be produced by such a sinusoid that is not exactly an integer multiple of 2 pi by n. Neither cos nor sine can be used. So what will be in that case? So in that case what will happen is it will obviously use cos and sine, but maybe not an integer multiple, maybe a fractional multiple. So it is between two integers. Okay, so এরকম যদি হয় তখন আমার কি হবে? So ওটা হলে যেটা হবে সেটা হচ্ছে the corresponding frequency domain representation of it, যে এফেক্ট আমরা দেখবো সেটা হচ্ছে instead of having a sharp peak like this, we'll have a peak with tails. So this is just the frequency domain characteristics of such a scenario. If the frequency exists between two integer multiples of basis functions, এটা হচ্ছে exactly on the basis function. In this case you'll get a sharp peak, and in the other case you will get a peak that creates some tails, that means a gradual peak, also a gradual fall of it. Okay, so this is the effect that you're going to get in the frequency domain. So এখানে যেটা দেখানো হয়েছে, the first sine wave is represented as a single point, the other peak is more difficult to understand since it cannot be represented by a single sample. মানে in the frequency spectrum it is not representable by a single peak. So এই জিনিসটা পিকটা এক জায়গায় উঠছে, বাট এটা মানে একটু kind of averaged out over this range. এখানে কোথায় exactly এটা শুরুটা হয়েছে এটা বোঝা কঠিন। Okay, so it will have some tails. So this is what we are referring to as tails here. মানে এই gradual increasing and decreasing region এটাকে বলা হচ্ছে এখানে tail, that it may extend a significant distance away. এই ক্ষেত্রে এটা মোটামুটি ক্লোজ ছিল, এমন হতে পারে যেটা উইথ অনেক বড় হইতে পারে। ওকে, এটা এরকম বড় উইথেরও হইতে পারতো। So the solution for this is to multiply the signal by a Hamming window. এটা আমরা অলরেডি দেখে আসছি যে আমরা আগে কেন করছি, এখন এটা এখানে বলা হচ্ছে যে হ্যামিং উইন্ডোর কাজটা কি। হ্যামিং উইন্ডো হচ্ছে এমন একটা মানে সিগন্যাল, মানে আমরা যেরকম বলে রাখি একটা প্রিডিফাইন্ড একটা ফাংশনের মতো, একটা ফিল্টারের মতো। সো হ্যামিং উইন্ডো ইজ লাইক একটা প্রিডিফাইন্ড ফিল্টার that if you plot it, it will look like this. And if you multiply it with any signal, what it does is, before doing the DFT, what it does is after you do the DFT, you won't get peaks like this. You won't get tails like this. You'll get peaks obviously in the correct locations, but you won't get tails like this. So the spectrum is changed in 3 ways by using this window. মানে এই হ্যামিং উইন্ডো মাল্টিপ্লিকেশনে তিনটা এফেক্ট হয়, তার মধ্যে দুইটা পজিটিভ একটা নেগেটিভ। সো উইল বি টকিং অ্যাবাউট देम নাও। So the first effect is that the two peaks are made to look more alike. So যেটা actual peak ছিল, that will become something like this, it will become a bit more widened. And যেটা actual peakটা পাওয়া যায় না, মানে there were some gradual increase and decrease here, that will also become like this. So they will become more alike. So এটাকে সে widen করে দেয়, and এটাকে সে যেটা wide ছিল সেটাকে সে narrow down করে একটা ক্লোজ রেঞ্জের মধ্যে নিয়ে আসে। ঠিক আছে, সো এটা হচ্ছে ফার্স্ট এফেক্ট অফ হ্যামিং উইন্ডো। The second effect is that the tails have greatly reduced. So instead of having gradual increase and decrease, it has a kind of sharp increase and sharp decrease, and that is what we want, because in the ideal case we will have sharpness instead of some gradual large width increase and decrease. So আমাদের টার্গেট হচ্ছে to decrease the peak width, পিকটাকে যত শার্প করা যায়, this is our target. So that is the second effect of হ্যামিং উইন্ডো। So this is also good. So এখানে কয়েকটা কথা বলছে যে this is good, this is good বলতে এটা actually first থেকে বলতেছে they are made to look more alike. So this is a good effect. The second is that the tails are reduced. This is also good. But the third effect is that the window reduces the resolution in the spectrum by making the peaks wider. So আমাদের যেটা করতেছি সেটা হচ্ছে আমরা একটা শার্প ইনক্রিজ শার্প ডিক্রিজ দিচ্ছি, বাট স্টিল এটার পিকটা খেয়াল করে দেখো, যেটা আগে অলরেডি শার্প ছিল সেটাকে একটু ওয়াইডার করে দিছে, এটাকে ঠিক করছে বাট এটাকে একটু ঝামেলা করে দিছে। সো এটা হচ্ছে থার্ড যে ইয়েটা সিনারিওটা, যেটা অলরেডি ঠিক ছিল সেটাকে একটু ঝামেলা করে দিছে, মানে সেটাকে একটু ওয়াইডেন করে দিছে। এন্ড দিস ইজ দ্য ব্যাড এফেক্ট ইন ডিএসপি জার্গন। The windows like the Hamming window, Blackman window, all of these windows provide a trade-off between resolution, that is the width of the peak, and the spectral leakage, that means the amplitude of the tails. তো স্পেকট্রাল লিকেজ বলতে আমরা যেটা বুঝাই সেটা হচ্ছে যে লিকেজ অফ স্পেকট্রাল ইনফরমেশন, মানে ফ্রিকোয়েন্সি ইনফরমেশন। আমরা এই ধরনের টেলস পাইলে it reduces our chance for getting good information from the frequency spectrum. আবার এই যে জিনিসটা width, যেটা having smaller width is better. So this is a kind of trade-off. We can reduce the tail, but we have to increase the width. So all of these windows like Hamming window, Blackman window, there are other windows actually, but এই দুটো mainly use হয় আর কি। চ্যাপ্টার 16 এ তোমরা এই দুটার ইকুয়েশন পাবা, if you are curious you can check that out. So these windows, they provide a kind of trade-off, and this is the trade-off that we are talking about. We want to reduce resolution, we want to reduce the width, increase resolution মানে to reduce the width, and we want to have more spectral information, that means reduce the spectral leakage. But window গুলো হচ্ছে একটা বাড়ালে আরেকটা কমায়, আবার এটা বাড়ালে তখন এটা কমায়। So এক একটা এরকম characteristics আছে। And which one will you use, Hamming window, Blackman window, or which one will you use? এই বিভিন্ন উইন্ডোর মধ্যে কোনটা ইউজ করবে এটা আসলে ডিপেন্ড করে হচ্ছে কোনটা কি ধরনের ট্রেড অফ দিচ্ছে। কোনটা দেখা যাবে যে রেজলিউশন বেশি দেয় বাট স্পেকট্রাল লিকেজ আরো বাড়ায় দেয়, অন্যটা দেখা যাবে স্পেকট্রাল লিকেজ কমায় বাট রেজলিউশনও খারাপ করে দেয়। সো কোনটা নিবে এটা ডিপেন্ডস অন দ্য সিনারিও। Okay, so now you can actually read through all this, but these are not necessary. There are lots of things here, mainly about the Hamming window and Blackman window. So which আমি এখানে যা যা বললাম আর কি যে কোনটা কি দেয় ওটা নিয়ে এখানে অনেক কথা বলা হয়েছে। So these are some examples of these things. Okay, there was also another window, এটার নামটা ভুলে গেছিলাম, rectangular window. There is Hamming window, Blackman window, flat top window. কোনটা কি ধরনের characteristics দেয় এটা নিয়ে এখানে কথা বলা হয়েছে, but that is not important. You can read through them if you want. So I'll be skipping through all of this, and I'll be going to the frequency response of the systems. So this is the part that we talked about, the second application of DFT, that is the frequency response. আমরা অলরেডি বলছিলাম যে টাইম ডোমেনে আমাদের কি হয়, টাইম ডোমেনে any signal behaves by convolution with h. Frequency domain, that same system will uh, behave using the frequency response instead of the impulse response. So this is the frequency response, and what it will do is it will perform multiplication. Here it does convolution. So this is the main difference. Okay, so any linear system can be completely described by how it changes the amplitude and phase of cosine waves passing through it. এই একই কথাটা মনে আছে, আমরা এর আগের চ্যাপ্টারে বলছিলাম যে any linear system can be completely described by how it changes the মানে how it behaves for a single impulse. মানে impulse responseটা কেমন সেটা যদি আমরা জানি, তখন আমরা পুরো সিগন্যাল সিস্টেমটা কিরকম বিহেভ করবে সেটা আমরা বলতে পারি। এখন আমরা বলতেছি ডিফারেন্ট কথা, এটা আসলে আমরা বলতেছি বিকজ এখন আমরা অ্যাজিউম করে নিচ্ছি যে we are in the frequency domain. So in the frequency domain, its behavior can be uh, described by how it changes the amplitude and phase of cosine waves passing through it. Okay, so this information is called the system's frequency response. And both the impulse response and the frequency response contain complete information about the system. So this one contains complete information in the time domain, and frequency response contains the complete information in the frequency domain. So there also must be a one-to-one correspondence between the two. So এখন one might expect যে তাহলে impulse response আর frequency response এর মধ্যে মানে রিলেশনশিপটা কোথায়? রিলেশনশিপটা যেটা সেটা হচ্ছে, let me just briefen this out. এখানে আরো অনেক কথাবার্তা আছে। The main thing is H থেকে capital H পাওয়া যায় by just performing DFT. So what is capital H? Capital মানে frequency response is just the DFT of the impulse response. If you perform DFT on the impulse response, what you will get is the frequency response. So প্রত্যেকটা সিস্টেম আসলে এইভাবেই ডিফাইন যে ও টাইম ডোমেইনে যেটা করে, যেটার সাথে কনভলিউশন করে, ও ফ্রিকোয়েন্সি ডোমেইনে অন্য একটা জিনিসের সাথে মাল্টিপ্লিকেশন করে। যে জিনিসটার সাথে মাল্টিপ্লিকেশন করে, that can actually be obtained from the impulse response by performing DFT. Okay, so they are related by a DFT and inverse DFT relation, IDFT. You can get one from the other by this procedure. You can get one from the other. Okay, so one will do convolution, the other will do multiplication. So এখানে যেগুলো বলছে, that is just the notation. Since small h was used for impulse response, capital H will be used for frequency response. And যদি আমরা এভাবে করে আউটপুটটা পাই in the time domain convolution, in the frequency domain input spectrum is multiplied by the frequency domain. Okay, so and remember that convolution and multiplication are not the same. Convolution is like multiply and add operation, আর multiply যেটা সেটা হচ্ছে element wise multiply. Okay, so now figure 9.7 shows an example of using DFT to convert a system's impulse response into frequency response. So you can look at this. So this just shows how you can go from one to the other, from the input to the frequency domain input, to the impulse response to the frequency response, and from the output to the frequency output. You can go from one to the other. So everything is actually, there is a correspondence between everything here. And okay, so now we are looking at figure 9.7, and then figure A is the impulse response of the system. So here, this is the time domain represent impulse response. এখন কথা হচ্ছে এই ইম্পালস রেসপন্স থেকে আমরা ইম্পর্টেন্ট ইনফরমেশন জানতে পারতেছি না যে এটা অ্যাকচুয়ালি কি মিন করতেছে, ঠিক আছে? সো ইফ ইউ লুক এট আ সিস্টেমস ইম্পালস রেসপন্স লাইক দিস, ইন সাম সিনারিওস আমরা হচ্ছে ইম্পালস রেসপন্স থেকে অনেক কিছু বলে দিতে পারি, আবার ইন সাম আদার সিনারিওস just by looking at the impulse response we cannot understand anything. For example, here you cannot understand what it actually does, but if you look at the corresponding frequency response, that means if you perform DFT on it, you'll start to understand important information about this system, what this system actually does. So এটা দেখে অলরেডি আমরা একটা গেস করতে পারতেছি, we can get a better guess if we pair it with a lot of zeros, that means increase capital N আর কি. So high resolution frequency response যদি আমরা নেই with a মানে large n, so we'll get this. Okay, so this is a bit more better looking frequency response. এখানে হচ্ছে মানে এদের স্পেসিং গুলো বড়, এখানে স্পেসিং গুলো আরো ক্লোজার. Okay, so this one actually gives us important information like what. So এখন এটা অবশ্য তোমরা হয়তো বুঝতেছো না, but you'll understand it later on when you study digital filter. So this one is actually the frequency response of a digital filter, of a band pass filter. Okay, So bandpass cannot. Notice that it passes frequencies from a bit below 0.2 to a bit above 0.3 of the sampling frequency. Okay, so this is a band pass filter. So এটা এতটুকু ফ্রিকোয়েন্সি হচ্ছে পাস করতে দেয়, বাকিগুলোকে জিরো করে দেয়, মানে বাকি ফ্রিকোয়েন্সি গুলো পাস করতে দেয় না। Similarly, a frequency response for a low pass filter would have been something like this. Okay, তোমরা হয়তো already দেখছো probably in your triple E courses. You might have already seen this. So this is the frequency response of a low pass filter. Lower frequency গুলো পাস করতে দিবে, higher frequency গুলো পাস করতে দিবে না। Remember the horizontal axis refers to the frequency. So these are the lower frequencies, these are the higher frequencies. So it is allowing these frequencies to pass and these frequencies to not pass. And this is the high pass filter. It is not allowing the low frequencies to pass, but allowing the high frequencies to pass. And this one is a band pass filter. So band pass filter, ideal band pass filter হচ্ছে এরকম হয়। This is not the ideal one. It gradually increases and gradually decreases. So these are just the ideal versions. Okay. So এটা থেকে আমরা যেটা বুঝতে পারতেছি সেটা হচ্ছে, in some cases time domain information does not give us time domain values do not give us much information, but frequency domain uh, amplitudes and all these things, the shape, the plot gives us important information. So এখানে এটাই বলতেছিল যে just looking at the curve, মানে the time domain impulse response curve does not give us important information, but taking the DFT of this produces the frequency response as shown in B, যেটা এখানে দেখলাম। Okay, so now the function of the system becomes obvious. It passes frequencies between 0.2 and 0.3 and rejects all others. So it is a band pass filter. So only after seeing the frequency response can you understand that this is actually a band pass filter. এটা দেখে কিছু বোঝা যায় না, বাট এটা থেকে ইজিলি বোঝা গেছে এটা হচ্ছে আসলে একটা ব্যান্ড পাস ফিল্টার। ব্যান্ড পাস ফিল্টার ইয়ে দেখাচ্ছিল, ইম্পালস রেসপন্স দেখাচ্ছিল। ওকে, so how much resolution can you so there are also other things যে আমরা এখানে যা যা বললাম প্যাডিং করে আমরা এটা আরো বেটার করতে পারি, এই জিনিসটাকে আরো বেটার করতে পারি, like here. So now the next thing is, how much resolution can you obtain in the frequency response? The answer is infinitely high if you are willing to pad enough zeros. There is, in other words, there is nothing limiting the frequency resolution except the length of the DFT. So এটার থেকেও বেটার করা পসিবল ছিল। তার মানে in the limiting case where there are infinite, the value of n tends to infinity, capital N tends to infinity, we'll get the best frequency response. So that is the actual frequency response, যেটা ডিজিটাল সিস্টেমে মানে হয় না। ডিজিটাল সিস্টেমে আমরা অ্যাকচুয়ালি অ্যাকচুয়াল ফ্রিকোয়েন্সি রেসপন্সটা পাই না। আমরা যেটা পাই সেটা হচ্ছে a kind of approximation of the actual frequency response. The actual frequency response would have been continuous, মাঝখানে কোনো গ্যাপ নেই, the samples would have been continuous. Okay, so now this can be better understood by bringing in another member of the Fourier transform family, the discrete time Fourier transform. So এটা আনার মেইন রিজন যেটা বলা হচ্ছে, that is because if you remember আমরা হচ্ছে চার রকমের Fourier transformer কথা বলছিলাম। এর মধ্যে দুটো ছিল কন্টিনিউয়াস, দুটো ছিল ডিসক্রিট। ডিসক্রিট যে দুটো ছিল তার মধ্যে একটা ছিল হচ্ছে ডিসক্রিট টাইম ফুরিয়ার ট্রান্সফর্ম ডিটিএফটি, আর একটা ছিল ডিসক্রিট ফুরিয়ার ট্রান্সফর্ম ডিএফটি। সো এই দুটোর মধ্যে ডিফারেন্স কি ছিল? ডিটিএফটি অ্যাজিউমড ডিটিএফটি ওয়ার্কড অন infinite signals aperiodic. Okay, aperiodic, and DFT worked on infinite মানে okay, so DFT worked on periodic signals. So this was the main difference between them. Okay, and also another thing is that আমরা DFT করার সময় একটা finite length নেই, n এর ভ্যালু মানে finite হয়, so it worked on finite length signals. DTFT worked on aperiodic infinite length signals. So আমরা এই DTFT কেন আনতেছি এখানে? That is because in the limiting case DFT can become DTFT. So this one works on infinite signals and aperiodic signals, right? So periodic কে কেমনে aperiodic বানানো যায় সেটা আমরা এখন এটা নিয়ে জাস্ট একটা theoretical discussion আর কি এখানে. So that is remember from the last chapter that DFT considers the time domain signal to be infinitely long and periodic. আচ্ছা, infinitely long সেটা কেমনে? That is by repeating the endpoint signal over and over. So even though we take endpoints, it repeats it over and over to make it infinitely long, but it is periodic. Okay, because it repeat করতেছে, আমরা same জিনিসটাকে repeat করতেছি, that is the endpoints are repeated over and over. Okay, so that is how it makes the infinitely long signal periodic. But the DTFT considers that this is not periodic. So how can we make it make DFT to DTFT? If we take this idea to the extreme, that is adding zeros, আমরা যদি zero add করতে থাকি, then the period of the time domain becomes longer. Okay, so suppose this is your period, so this is the endpoint. You take this shape, and what DFT will do is it will make infinite periods like this, each of the same shape. Okay, uh, so মানে এটা এভাবে রিপিট হতে থাকবে আর কি। So from one period like this, it will make infinite periods like this. So now if you start adding zeros to one of these periods, what will happen? The length of this period will become larger, right? So if you start adding zeros, so এখানে অনেকগুলো জিরো করলাম, অনেকগুলো জিরো দিয়ে, so this becomes one period. So now the next period also will become large like this. Okay, এটারও লাস্টের দিকে অনেক জিরো থাকবে। ওকে, সো এভাবে করে এখন আমরা সবগুলো পিরিয়ডই একইভাবে চেঞ্জ হয়ে যাবে ডিএফটির ওই রিপ্লিকেশন মেথডটার কারণে আর কি। So now if you extend this idea to the extreme, okay, so এখানে যেটা বলছে যে if you take this to the extreme by adding infinite number of zeros to the time domain signal, then what will happen? If you add an infinite number of zeros, then it becomes aperiodic, because আগে হচ্ছে আমরা একটা finite number of zeros দিছি, so our period ended at one point, so we could again start it and give a finite number of zeros and end another period, right? But now you're adding an infinite number of zeros, so there is only one period. There cannot be more periods, more repetitions like this. There can be only one period, and that will extend towards the infinity. And so ultimately that means what? That means we have an aperiodic signal. We do not have multiple periods anymore. So thus periodic, in other words, it is turned into an aperiodic signal. If you give infinite number of zeros, then this the periodic signal approaches towards aperiodic signal. So then it starts then DFT does not apply on it, then it DTFT applies on it. So this is how any signal যেটা হচ্ছে আমরা DFT অ্যাপ্লাই করতে পারি, সেটাকে আমরা যদি এক্সট্রিম আইডিয়াতে নিয়ে যাই তখন এটার উপর DTFT অ্যাপ্লাই করা যায়। So this is just the theoretical discussion. Ultimately আমরা কিন্তু DTFT কখনো অ্যাকচুয়ালি কম্পিউটারে অ্যাপ্লাই করতে পারবো না। আমরা অলরেডি বলছি কেন সেটা, because a computer cannot store infinite number of samples in the frequency response. We cannot have infinite number of samples. That is why we ultimately use the DFT.
ভাই আমাদের একটা ল্যাব আছে এখন।
আচ্ছা, অলরেডি 12টা বেজে গেছে, তোমাদের এটার পর আরেকটাই আছে I guess. So okay, we'll be ending the discussion here. We have one more topic actually after this. This is the last topic of this chapter, convolution via the frequency domain. Let me see how big it is. Okay, so this is just the last topic that we have left, and we'll be finishing it in the next on Monday. Okay, so this is all that is up for today. I'll be stopping the screen share.